In this section, we want to start things off by looking at how polynomial models can be used to look at problems involving optimizing revenue. In example 1, we're told that the price P in dollars and the quantity sold, X, of a certain product obey this given price demand function. P equals -1/6 X plus 200. This expression, this equation, is actually a linear equation. What we're looking at is polynomial models. So one thing to keep in mind is we're going to modify this given price demand function to generate a polynomial. In part A, we want to find a model that expresses the revenue R as a function X. So revenue can always be thought of as price, so how much we charge per item, times the number of items that we sell, which is the same thing as demand. In order to calculate price times demand, what we can do is take the linear function above that we were given, P of X, times X, which is our demand, or the number of units produced and sold. This is going to give us -1/6 X plus 200 times X, or a revenue function of -1/6 X squared plus 200x, once we take that x and distribute it through both terms of that price demand function. Now what we have is a polynomial function, though technically we had a polynomial function before, since linear functions are just special cases of polynomials where we have a degree 1. But now we have a polynomial function, specifically a quadratic function, with an x squared term, and we're next asked, what is the domain of R? There's nothing really for us to calculate here. This is more of an interpretive statement. In this case, we would want our domain to be 0 to infinity, with a square bracket at 0, meaning 0 would be included as part of our domain. And we arrive at that by thinking just intuitively about our value for X. This is our number of units sold. We can't sell less than 0 products. We could sell 0, and then we could sell, in theory, an unlimited number of products. We're asked what's the revenue if 250 units are sold. In order to find this, we would simply evaluate our revenue function, which we've now found, at x equals 250, which would give us a value of approximately 39,583 or $39,583.33. Next, we want to find and interpret all extrema of our revenue function. So switching to Desmos, we can input that revenue function. And then adjust our viewing window until we start to see the shape of that parabola. I'm going to go ahead and adjust my x min and x max so that we can get an even better view here. And clicking on our graph will reveal that that absolute maximum is occurring at the point 600, 60,000. Which tells us that our maximum revenue of $60,000 is achieved by producing and selling 600 units. In part E, then, we're asked what price the company should charge to maximize revenue. To answer this, we'll go back to the given price demand function. And what we'll do is plug in a value for X, which is the number of units sold, and that will generate a price point, P, that we would want to associate with that selling point, or with that number of units. So what we'll do is evaluate P at x equals 600, which is obtained from that maximum value that we identified, to get a price point of $100, meaning what we're considering in this problem would be selling 600 units for $100 a piece to achieve that maximum revenue of $60,000. Example 2 is very similar, but we need to start things off a little bit differently here. What we're given is still a price demand function, but in this case it's solved for x instead of p, meaning our first step is going to be to take this equation and solve it for p. We can do that by subtracting 88 from both sides and then dividing both sides by -4 to get p equals -1/4 x plus 22. From there, the problem follows pretty much identically. To get our revenue function, we'll take x times that given price demand function. So this will be 1/4 x squared plus 22x. We want to find and interpret all extrema. In this case, that would be at x equals 44, y equals 484. And our interpretation would be the same as above. When we produce and sell 44 units, we achieve our maximum revenue of $484. To identify the price point that we should be selling these items at, we would substitute x equals 44, which is the value we would have found from that absolute maximum point, which would give us a price point of $11 per item. And then in part D, we're asked something a little bit different. What price should the company charge to earn at least $288 in revenue? To answer this question, we'll enter our revenue function into Desmos. What we're interested in is a revenue of at least $288. So what we're going to do is enter in a new function, y equals 288, meaning what we're looking for are values that are above this line, and values above that line are achieved when x equals anything between 16 and x equals 72. So we're achieving that revenue of $288 or more whenever we're selling between 16 and 72 units. What we can do then is take those values and substitute them into our price demand function, which would generate price points of $18 and $4. Meaning if we want to achieve that revenue of at least $288, we're going to have to sell our product for anywhere between $4 and $18.